Elastomeric components are part of the many practical product design that's being made. Elastomers serve one or many purposes in the products that's being sold to the customers. Either they introduce some flexibility between the components, or it serves the purpose of sealing. In some places it also serves as a vibration isolator. In some places it is acting like a non-load carrying member such as dust cover, etc. There are some applications where the rubber or elastomer component is the primary load carrying member, such as a basketball or a football or a hot air balloon, and etc. I hope you all are working in one or other areas of rubber analysis and design. I deeply thank you all for taking your time in attending this 2-hour webinar on material modeling aspects of elastomeric components and some aspects of metals. Part 1, we covered various aspects like basics of stresses, the importance of volumetric and pivotric components, and also we discussed about the invariants, different locking mechanisms, and different element formulation which one need to know when you are planning to analyze elastomeric components or incompressible materials. At the end of the part 1 of the seminar, I promised to do second part of this series, majorly covering material aspects of modeling elastomeric components. So today we will be talking about basics of hyperelasticity. We will be distinguishing the physics and mathematical aspects between regular elasticity and hyperelasticity. We'll be discussing about strain energy density functions. We will also be talking about different types of constitutive models. We will also be going through different types of tests that we need to conduct to analyze elastomer kind of a material. We will also be talking about the curve fitting techniques and the consideration for using the test data. And also we will be giving you a very generic guidelines on which material model to use for given situation among the many different material models available in Ansys. And also we will be talking about how to model a stress strain curve which looks different in tension and compression. Some kind of non-elastomeric components like metals or plastics do exhibit different stress strain behavior in tension and compression region. We will be touching upon that. And also we will be talking about some rate dependent phenomena like damage or softening, or how to predict the permanent set, and so on. Like part 1 of this seminar, in this webinar mostly we will discuss about usage aspects, meaning to gain more insight about the materials rather discussing about software procedure aspects. So how do I go and set this particular thing in Ansys software? Those procedural aspects are addressed through other means of support that you can get from Ansys, either through regular trainings or customized training or through regular technical support mode. Let's get started. When we say rubber or rubber-like components like elastomers, which commonly encompasses the thousands of different types of rubber components, typically a rubber chemist or a designer deals with. When you are dealing with design of elastomer components, the view for designer and the view for analyst who models using FEA or some other numerical technique is quite different. There are standard design guidelines available through literature. Say if you want to design a rubber seal for a elevated temperature application, there are certain formulation on rubber which shows good thermal resistance compared to the other rubber. If you are using this to seal a particular chemical fluid flowing through the piping system, there are some other chemical component of the rubber which offers good chemical resistance compared to the other type of the rubber. So what type of chemical composition need to be chosen for a particular design, it depends on which operating environment it is going to work. That's the designer point of view. In analyst point of view, once a particular chemical composition is chosen, then the analyst is going to understand what are the material characteristics for that particular rubber component and how do we capture deformation under given loading condition, how do we capture the stresses, the strain that get induced in the rubber component because of the different applied loading. So in this webinar, we are going to majorly focus on the analyst view of elastomeric components, which will encompass all different types of chemical composition which are normally put under a category within the double codes called elastomeric components. Long ago, once upon a time, there were two kinds of people, physicist and mathematician. Initially there were no engineers. So the physicist and mathematician started looking at the material in two different aspects. So the physics, or in the physical meaning, the elasticity is defined as when we apply a load on an elastic material, if the material is elastic, upon unloading, the material comes back to its original state. That's the physical definition of elasticity, or a material which is elastic in nature. But in terms of the mathematics, it is viewed slightly differently. As we are all engineers, dealing with equation is quite inevitable. In this webinar, I try to make the equation as simple as possible. Some of the equation that you may see in this slides may violate or may slightly different from the exact mathematical convention that's supposed to be used, including the tensor notations or the indices and so on. When we look at the equation, typically in any continuum mechanics course, which is quite complex and which is quite detailed, because of the reason that the continuum mechanics equations bring in the generality, which means that those equations can be applied to any types of the structure. At the same time, if we look at the equation that comes into strength of materials or solid mechanics, the equation looks quite simple because it is the derivative of the generalized equation that we commonly see in the continuum mechanics aspect. So in either way, we can look at as a top-down approach from the continuum mechanics to the solid mechanics, or the bottom-up approach from solid mechanics to the continuum mechanics. In this webinar, I try to make the equation mostly in solid mechanics approach, so that it gives some physical meaning rather than these being mathematically correct. Okay, having said that, in terms of the math, if we can write a strain energy function for a material, and if we differentiate that strain energy function with respect to strain, and if we are getting a stress that exists in the material, then we can say those materials as elastic materials. Okay, that's the definition. Now let's look at in simple solid mechanics approach, we all should be familiar with this approach. What is strain energy density function? It is nothing but the area under load displacement curve. So one can write the area under load displacement curve as a triangle. Then we can say the area of this triangle is nothing but of force into the displacement. So this is nothing but the strain energy. When we say the density, the strain energy is divided by the volume, so that the A and L of this particular rod, assuming it's having a certain cross section and having certain length, and we can say volume as A into L, and this F by A gives the sigma, and change in length by the original length will give you the strain. So now the strain energy density function can be written in terms of the stress strain curve or in terms of the force displacement curve. So the either way is possible. We also know the basic relationship between the stress and strain. Here the stress can be written as force by area, and the strain is nothing but it is in the denominator, so it's original length by change in length, which can be manipulated like this. It means that the change in length or the displacement can be written something in terms of the geometric attributes. These two are the geometric attributes. This is the material attribute. This is the external loading attribute. So now, having understood this, we can say the strain energy as of stress into strain. Stress can be written as in terms of the Young's modulus. So if we differentiate this with respect to strain, what we are going to get is the stress. So this is a simple understanding of how the mathematical definition of elasticity is used in deriving basic solid mechanics approach. If we are dealing with highly nonlinear materials like elastomers or rubber, the approach is going to be the same, but the mathematics will become slightly complicated. But the foundation is this: whether it's a simple elastic material, 1D structure subjected to the axial load, or it's a very complicated rubber boot which is having very complex stress strain curve, and we need to carry out a very complex analysis. Before we get into that, it is important to have a feel for how elastomeric materials are different from a normal metal, because most of the engineers are very much familiar with how metal behaves and also have a physical feel for the metal rather for elastomeric materials. When we do most of the analysis, the ultimate objective oftentimes would be make sure the part or the structure not going to break. If you take a typical metal which breaks into pieces, typically in the strain range of 10 to 30%, but when we talk about the elastomers like rubbers, it can undergo very large strain, probably in the range of 300% or sometimes even something like 700-800% without the material being cut into pieces. When we are having a large difference in the physical aspect, one need to keep in mind that the same mathematical aspect which is used for the metal cannot be used for the elastomers as well. We need to take different mathematical aspects. Okay. Now let us look at in terms of the stress strain curve. For any typical metal, we will have a linear portion within which it will obey a Hooke's law. After that, beyond its yield stress, the material start going into the plastic range, and we use a plasticity law to capture the response of the material in this particular range. So for linear region, we use Hooke's law, which is quite familiar. For plasticity zone, we use something called as flow rules to capture how the plastic strain is going to increment as the load is being increased. Since the physical behavior of the metal is quite different from elastomers. We can't use the same mathematical aspects to capture the response of the elastomeric materials because in metal, whatever the deformation that is happened in the plastic zone, which is not recoverable, when we unload the structure, the unloading pattern might happen somewhere here. There will be certain amount of residual deformation left in the structure even after we unload the structure. But in case of a hyperelastic material, the entire deformation or the strain is elastic. Even though it undergoes very large strain, upon unloading, the material is going to come back to its initial position. So the first difference need to keep in mind, for metals in the elastic region, there is only one slope which can characterize the entire stress strain behavior, that is the Young's modulus. For rubber kind of a material, though the response is elastic, along the load path there is no single slope or there is no single elastic modulus which can relate the stress and strain. Along the load path, the moduluses or the elastic modulus are going to keep changing. So in order to characterize this behavior, rather we use the Hooke's law approach, we are going to take a strain energy approach that we discussed in the previous slide. So the S here means the stress, and this is the strain energy, and this is the strain. So when we can write a strain energy density for any material in terms of the displacement or stress and strain relation. If you take a derivative of this, we are going to stress. So in mathematical aspect, hyperelasticity mathematically means it's a property of the material which are described in terms of the strain energy function. So if you look at any material constitutive law which is written in terms of the strain energy density function, then you can say that material as hyperelastic material in mathematical aspects. In physical aspects, hyperelastic material means it can undergo large deformation but which is still elastic, unlike metals. And upon unloading, it will follow the same path, and the stress at any particular position is a function of current state, so it is path independent. It doesn't mean we reach this particular path either in this particular way or in this particular way or this particular way. It is path independent behavior. On a macroscopic level, rubber exhibits certain unique characteristics. The first one is that metal is also showing a nonlinear behavior, but its strain range is very limited, up to which it's elastic, beyond which it is going to be in plastic zone. But still, in terms of the strain range, it is small percentage of the overall strain that any elastomer can experience. It can experience very large strain. And another interesting characteristic is that for many of the metals, the stress strain curve in tension region and the stress strain curve in the compression region is going to be the same or assumed to be the same for many of the practical purposes. But for many of the elastomers, the stress strain curve in tension region and the stress strain curve in compression region is significantly different. We cannot make same assumption like that of a metal. So these are all the challenges we are going to address in this presentation. Right. So mostly the physical behavior of the rubber, which is nothing but undergoing very large deformation, is due to the molecular structure of the rubber component. So So the mechanical property of an elastomer component strongly depends on the crosslink density, modulus and hardness. As the hardness increases, the crosslink density increases, and hence the material becomes more elastic, which means that it becomes more rigid. It is tending to, as the hardness increases, the behavior of the elastomeric component will tend to approach any metal. Okay, it will become less and less hyperelastic, but more and more elastic. The crosslink density really determines the physical behavior of the structure, which can be predicted in terms of the equation. So we are not getting too deep into the network architecture of the elastomeric materials. Rather, we will concentrate more on phenomenological aspects of the rubber material or the continuum mechanics of the rubber material. Though we use different material laws like Moody-Rowling or Ogden and so on, though they are written in terms of the strain energy density function, they have a strong relationship with the molecular structure of the rubber component. Say for example, for a 2-parameter Moody-Rowling material model, we can write stress as a function of its strain, which is a stretch ratio. From this equation, we can understand that the first material constant for a Moody-Rowling corresponds to crosslink contribution, and the second parameter, which is C10, which corresponds to the entanglement contribution in the rubber network. So these equations will become clear as we move on. Let's start gain some basic terminologies that we commonly use in hyperelasticity theory. Mostly when we deal with metals, the deformation is talked or discussed in terms of the strain. But when we are dealing with hyperelastic materials, rather using the strain, it is quite common to use something called as a stretch ratio, which is nothing but the ratio of deformed length over the original length. In terms of simple equation, the stretch ratio is nothing but 1 plus the engineering strain. When we are dealing with hyperelasticity, we often have to deal with terms like engineering stress strain curve and the true stress strain curve. So it is highly advisable to familiarize the relationship between engineering stress strain curve and the true stress strain curve. So having understood the stretch ratio is nothing but 1 plus the engineering strain, in the part 1 of this presentation, we have discussed in detail about something called principal stresses, principal strain and invariants. Same like principal stress and principal strain, we could write the principal stretches in all the 3 directions. Principal stretch lambda 1, lambda 2 and lambda 3 and so on. And by now it is clear that when we are dealing with hyperelastic materials, the constitutive equation is in terms of the strain energy potential, not directly in terms of the stress and strain relationship. So one can write the strain energy potential either as a function of 3 principal stretches or as a function of 3 strain invariants that we have seen in quite detail in part 1 of this series. So once we have the strain energy potential, it is possible to get the stresses that is induced on the structure by differentiating the strain energy potential with respect to the strain, or with respect to the strain is eventually nothing but the strain can be related either to the invariance or to the stretch. There exists a relationship between strain and the stretch and the invariance. And another important aspect that we have seen in the part 1 of this series is the incompressibility aspect of elastomeric materials. So the incompressibility aspect is mathematically formulated in terms of the volume ratio, which is nothing but ratio between the initial volume and current deformed volume. Especially when we are dealing with elastomer seals used in high temperature sealing application, there is a huge amount of volumetric strain due to the thermal strain that is induced. If there is any thermal strain induced in the elastomeric material, the volume ratio is calculated as per this particular equation. So again, when we are dealing with incompressible materials or nearly incompressible materials, we have discussed the importance of separating deviatory component and volumetric component in part 1 of this webinar. The same logic is maintained in the material formulation level as well. So out of the total strain energy density, which is split into deviatoric part and volumetric part, whether it be in terms of strain invariance or in terms of the principal stretches. So the D component corresponds to the deviatoric part, and B component, which is nothing but the change in volume, is separated in terms of the volume ratio. Okay, let's look at how we are going to write strain energy density function for any given material. So the strain energy density is function of 3 invariants, so which can be related to a Taylor series expansion, which is going to contain which is the function of the first invariant, second invariant and third invariant. They are carefully chosen such that the I minus 3 is nothing but when there is no deformation, this term will become 0, okay, because I1 is nothing but lambda 1 square plus 2 square plus 3 square, it will become 3 when there is no deformation, and this I1 will become 3 minus 3 it will become 0. So when there is no deformation, there is no strain energy potential in this material. And also this can be expanded like a series, and depending on how complex the stress strain curve, the power of the invariant is going to keep increasing. If the material is incompressible, then there is no volume change and I3 becomes 1. This equation gets reduced to this form as this term turns to 1 and we get eliminated, and we end up having a equation something like this. For example, if you are already started working with rubber or elastomeric materials, you must have been familiar with something called 2-parameter Mullins model, which typically looks like this. This 2-parameter Mullins model is basically derived from this equation. So what we are doing is that we are going to take only one term here, mnk, the summation should be 1. So we are going to take 1 and the k becomes 0 here, and we can write C11 and the second term will become C01, okay, mn and the next term nm. And because when this term goes to 0 and this term goes to 0 and we end up having this equation, this is what we call it as a 2-MR Mullins equation. I have shown this from this equation without considering the compressibility effect. If there is a compressibility effect, we could account adding a volumetric term to this equation so that we can account small amount of compressibility that exists in the material. Having understood the foundation for writing strain energy potential for any hyperelastic material. Now, the strain energy potential can be broadly categorized into three categories. There are many material models available to model hyperelastic material. There are more than 10 different materials available. So these materials can be grouped into three categories as shown here. The first one is the statistical model. So the statistical model really looks at the molecular aspect of the rubber material and assumes that there are molecular chains and the material deformation is happening due to the stretching of these molecular chains. So the way in which how many molecular chains are considered for a unit cube, based on that there are 3 parameter molecular chain model, there are 4 parameter molecular chain model, there are 8 parameter molecular chain model. So the only key takeaway from this particular slide is that if there is any material model which is statistical in nature, they are coming from the molecular aspect of the elastomeric material. The another category of material model is called phenomenological material model. In this particular category of the material model, we don't look at the microscopic aspect of the elastomeric material, but rather we will look at the material in continuum mechanics point of view. We are not really bothered about what is the atomic structure or molecular structure inside the material, but we will be looking at as a block box, and if we apply some if we induce some strain, what is the stress that is going to happen in the material, like how we deal with any metal. Okay, so we look the material as a block box. We don't want to understand the molecular structure of the material. There is a third category of the material models which are called as response function model. So here, instead of we looking at the material constant, what we do is that we will take the direct derivatives of the strain energy potential to determine the stress. The biggest advantage of response function model is that we don't want to really do a curve fitting procedure to find out the coefficients, like what is this C10, what is this C01. We don't want to really worry about finding out those material constants, whereas these two material models really call for finding out those material constants through curve fitting procedure from the experimental data. But the response function model will straight away can calculate the stresses from the experimental data by bypassing the curve fitting procedure. We will discuss in detail about the response function in later slides. So the choice of what material model to choose will depend on the type of the elastomer. Like in the first slide I have shown, there are different types of elastomers, NBR, SBR, EPDM, there are so many categories. First it depends on the type of the elastomer. Then the amount of loading, how much percentage of strain that your elastomeric component is going to see. And more importantly, what are all the material test data available with you? Okay, in coming slides we will talk about what are all required data to characterize elastomeric materials. There are certain situations that one may not have all the required test data. There was out of 6 different data that one needs, you may be having only 2 or 3. How do we deal with only those available material data? Okay, so we have seen many different material models. oftentimes one or more material model will capture the same behavior. So it doesn't matter whether you use material model A or material model B. But there are certain situations where your stress strain curve can be captured by only one specific material model. You have to really identify which model is going to capture. In some situation, if you have a stress strain curve, more than one material model can capture those stress strain curve. Okay, we will talk about that detail in coming slides. So when you choose a particular strain energy potential function, and the number of material constant you need to find or derive from the test data depending on what strain energy potential is being chosen. And what we are going to do in this presentation is that we are going to go through different strain energy potentials or different hyperelastic material models. We are going to give you some very generic guidelines under what situation what material model is found to be suitable. Again, remember that these are guidelines, not the rules. Okay, these guidelines may not cover all the 100% situation. Okay, the very generic hyperelastic potential model is called polynomial form, which is written in this particular form, which is a function of first invariant and the second invariant. Here, the order of this polynomial can go to any number. It can go to any particular power. You can keep expanding this with 1, 2, 3 and 4. Depending on how complex your stress strain curve is, we have to increase the order of polynomial has to be used. This is the more general form. Okay, I again want to pause here for a few seconds so that you can get a feel for how you can expand this equation for multiple terms. Okay, you can say C 0, 1 and second case 1, 0 and so on. You can keep expanding, and this portion corresponds to the deviatoric part and this portion corresponds to the volumetric part. So many of the material models that we are going to see in the coming slide is nothing but the derivative of this particular polynomial form of hyperelastic function. Here are some guidelines for choosing what order of polynomial has to be used for a particular rubber component which is exhibiting a particular shape of the stress strain curve. Okay, now let us look at this particular curve, which is quite simple. There is no inflection point. I hope you all know what does inflection point means. Inflection point means there is a discontinuity in the slope of the curve. Those points are called as the inflection point. So this curve doesn't show any inflection point. This curve shows one inflection point and this curve shows two inflection points. The order of the polynomial really depends on how many inflection points or how complex your stress strain curve looks like. To put it in another simple form, here is, let's say you can take this as a y and x axis. So what we are going to write, we are going to write y-axis as a function of x-axis. We are going to write stress as the function of strain. But here, if it is a linear stuff, the order of the strain is going to be 1. Depending on the shape of the curve, if the shape becomes more and more complex, we have to increase the order of the strain. Okay, up to which order we are considering the strain. You may wonder, in this strain energy function, where is strain coming? We are not using the strain anywhere here. But remember that this invariant is nothing but a function of stretch, but the stretch is nothing but the function of strain. So look at this. Let us look at this particular term. Okay, so this is nothing but 1 plus strain square. Okay, this particular term is nothing but this square. So if the strain is captured with more and more power, the square time again keep going. So the order up to which we are considering the strain in this equation is increasing. As the strain increases, you have to use more and more order of the polynomial. The most common form is that we use either 2 or 3, which can capture up to 100 to 300% of the gain time. Okay. When we use the polynomial order more than 3, though it can capture very complex stress strain curve, but mathematically the curve fitting procedure and other thing becomes very complex. So one of the challenge here is that as we are going for higher and higher order of the polynomial, we need data for all the modes of deformation. We need the stress strain curve in the tensile direction, in the shear direction, or in the biaxial direction, and so on. So if you have only uniaxial tension test data, you don't have a shear test data, or you don't have a biaxial test data, in such a case, and also your the tension stress strain curve is more complex, it is not really recommended to use higher and higher order polynomial using this particular polynomial form material model. Rather, it is recommended to use Yeo material model, which we will be discussing in coming slides. Okay, now let's look at the Mooney-Rivlin material model. I will first explain the second 2-parameter Mooney-Rivlin material model. In the previous slide, for a general form of polynomial form, this n can take any particular value. But in terms of the Mooney-Rivlin 2-parameter model, this n is limited to 1, so it is eventually nothing but a derived form of the general polynomial model. So when you substitute this I and j here, this Cij becomes C10 and this becomes C10 for the next term, and also you have the volumetric term of that. So later you will see that the C10 is nothing but the derivative of this strain energy function with respect to invariant. I will show you how exactly we reached to this point through a derivation in later slides. And again, it's important to note that now you may wonder why this 3 coming from, where is this 3 coming from? This 3 is make sure we get this term to 0 when there is no deformation happening in the structure. And also it is important to realize that for many of the metals, by looking at the Young's modulus, one can say whether the material is relatively harder or stiffer. But looking at this value of C10 and C01, it is very difficult to have a physical feel. But however, we can say the initial shear modulus as per this, it will be twice the sum of C10 and C01, and the bulk modulus can be related to this. And again, using the simple relation, we know that the Young's modulus is nothing but 2 times the g of 1 plus mu, and when we have for incompressible material, this mu becomes 0.5, and so that we will get Young's modulus as 3 times the shear modulus. And same way we can get the bulk modulus also in terms of C1 and C0 and the Poisson's ratio. Okay, in Mooney-Rivlin model itself, there are 2-parameter model, 3-parameter, 5-parameter and 9-parameter Mooney-Rivlin models available to capture more and more complex stress strain behavior. But all these forms are nothing but the derivative of general polynomial form. When we keep n equal to 1, we get this 2-term Mooney-Rivlin model. When we keep n as 2 and we make these 2 terms 0, then we get the third order or 3-term Mooney-Rivlin model, which requires 3 input parameter. Okay, that's why we call it as a 3-term Mooney-Rivlin model. And also when we use n equal to 2 but we don't make these terms as 0, we end up having 5-term Mooney-Rivlin model. And also there is a 9-term Mooney-Rivlin model when we make n equal to 3 in this general form of a polynomial model. Now there are certain guidelines for choosing a Mooney-Rivlin model. Remember that the Mooney-Rivlin model is nothing but same as that of a polynomial form with different orders of the polynomial. So whatever we have discussed or whatever the guideline we have seen for a polynomial form, the same is applicable here. Higher the order, more the complex stress strain curve we can capture. But more often used Mooney-Rivlin material model is the 2-term Mooney-Rivlin model. Here are some very broad rules of thumb. Again, remember that this is just the rule of thumb, not the strict rules. The 2-parameter Mooney-Rivlin model can be used up to 100% tensile strain. Although it will not account the stiffening effect, okay, because we are using only n equal to 1, which cannot capture the complex curve which requires the higher order polynomial to capture the curve. So if you have the stress strain curve showing this kind of a response, then using the 2-parameter Mooney-Rivlin model is not good, but it may be good up to this point. You can use that. Probably this curve can be captured using the polynomial order of 1. Okay, remember that when we say the polynomial order of 1, it is not strain with order of 1. Okay, the strain will have a different order because the strain is related to your lambda will have powers and so on. This is for the tensile, and for pure shear it can be used up to 90%. For compression, it is good only up to 30%. Okay, if you are having any component which is undergoing a very large compressive strain, then this is not recommended material model. But in general, many of the rubber materials are limited to 30% of compression, okay, because many of the design guidelines say the maximum allowable compression is something around 25% or 30%. Okay, next, Yo model. Yo model is another form of the reduced polynomial model. If you have the polynomial order of 1 and if we make the second invariant term 0, then we get Yo polynomial here. Okay, we are just making this term 0 so that it will become simple. Again, the Yo polynomial can have a different order. The commonly used Yo model is with polynomial order of 3, so that it can capture a little complex stiffening behavior with cubic form. Okay, and also here the initial shear modulus and the bulk modulus can be related with this. The reason I have been repeating the initial shear modulus and the bulk modulus is that though the stress strain curve looks really complex, at the beginning there would be a small portion where it is going to be a linear. From this you can calculate manually what is the Young's modulus. From the Young's modulus is nothing but 6 times the G. Young's modulus is 6 times the G if the material is assumed incompressible, so that you will get a feel how good this constant relates to your actual material behavior. Here are some guidelines for Yo model. The second invariant is omitted because it comes from lot of experimental justification that at the higher strain range, the influence of the derivative of the second invariant is much small compared to the influence of the first invariant. So at the very large strain, if you are interested to accurately capture the behavior at large strain range rather at the small strain range, then this becomes a very suitable material model. This really works good if you have only one uniaxial test data. You don't have other test data, but you have only one test data. This works really good. And also, when you are using a 3-parameter Yo model, there will be a 3 constant. The C10 is positive. This captures the initial response in this region. If C20 is negative, then it captures the softening behavior in your stress strain curve. Again, C30 is a positive. This is going to capture the hardening behavior of your stress strain curve. So the reason for giving this is that later it will become clear when we do the curve fitting, especially the outcome of the curve fitting depends on what initial value we are going to provide in the iterative process. So these guidelines can be used to provide the initial guess value for those curve fitting procedures. Neo-Hugin is another form of or in other words reduced form of a 2MR model. If we make the second invariant 0, we get this. Again, this is one of the very simplistic material model. It requires only one material constant as an input. So although this is a phenomenological material model, the shear modulus can be related to the molecular aspects of the thing. So though remember that though we categorize the material models into statistical models and the phenomenological model, the physical behavior of the material is same. So whether we use statistical approach or the phenomenological approach, the prediction should be the same whatever that happens to the physics. So the statistical approach and the phenomenological approach are only the mathematical aspects. Eventually they lead to converge to the same physical behavior. So one example that we can see is here. Okay, in this case this C10 corresponds to the molecular physics of the elastomeric material. So here are the guidelines. This is very simplest hyperelastic material model. If you have no prior experience in dealing with hyperelastic material model, this is the first model you want to start with and do various trials, errors, and understand how the hyperelastic material is going to behave. The guidelines are, it is good up to 30 to 40% of the tensile strain. For shear, it is good up to 70 to 90%. For compression, it is very moderate, up to 30%. However, it will not capture very significant change in the slope of the compressive region. Okay, in that case, this is not a recommended model. The reason why pure shear can capture larger strain range compared to the tension is that for tension, the stress strain curve may start nonlinear from the beginning, but for shear, most of the time from the test it is seen that mostly it will obey kind of a simple nonlinear rather being a complex nonlinear. That is the reason for many of the material model, pure shear mode can be captured for a higher deformation range compared to the tension. The Aruda boys is another hyperelastic material model. Unlike the previous material model that we have seen, which are phenomenological, this is a statistical chain network based material model. As I mentioned, there are different chain network material models based on 3 chain, 4 chain and so on. This particular Aruda boys is nothing but 8 chain network model that is implemented in Ansys. The strain energy potential for this particular material model is given in this form, and again, unlike in other material models where one need to find out from the stress strain curve what are all these constant values. But for Aruda boys material model, these constants are already predefined, so it is fixed. Again, this material model is found to be good only when you have limited test data, because we need only few material parameters, and most of the material parameters are already predefined. The another important feature of this Aruda-Boyce material model is that there are some material model which will show very steep hardening behavior, something like this. After a particular strain, the stress will increase, or the material becomes very stiff, and it may lead to the infinite stress to go beyond the particular deformation. So that particular value is called limiting stretch value. So if any material model that shows this kind of steep stiffening behavior, then it is recommended to use Aruda-Boyce model. Okay. So if the material is showing some kind of not a very stiffening behavior like this, but like this, then this may not be very useful. But if it is showing a very steep stiffening, this material model becomes a very useful model. And also this is very suitable for large strain ranges, okay, because typically this would happen after reaching a particular strain. If you want to capture this behavior, it becomes very useful. And another important limitation this model is that it is not capable of capturing the softening that happens here in some material, but it is very good at capturing the stiffening but not softening. If your product is working in this particular range, then this material model may not be good. But if your product is working in this particular strain range, very large strain range, then this material model is the recommended material model. Gent model is another micromechanical based model which is similar to Aruda-Boyce, but there is a difference in the limiting value. At what limiting stretch value your stress stiffening is picking up. Here are some guidelines for Gent model. So this is here the expansion is performed based on the logarithmic form, so that the resulting formulation will become similar to the Yo model, but however the coefficients are predefined function of the Jm. So it may not be it may not suitable for all different types of the stress strain behavior, but for whatever the stress strain curve which fits with this predefined function, for that this is a really good model. Okay. So this is almost similar that of the Aruda-Boyce model, and it can be thought something similar to a Yo model as well. This is again really good for large strain cases. Let's look at another form that is called Ogden form. So Ogden has the difference of this Ogden form is that in all the previous form we have seen that the strain energy function is written in terms of the invariance. Okay, so if you look at all these forms, everywhere the invariance is used to define the strain energy potential. But in the Ogden form, instead of using the invariance, the principal stretches are directly used. That's the one difference in Ogden form compared to the another form. In Ogden form, there are two variants. One is incompressible or nearly incompressible, wherein the incompressibility is separated from the deviatory component. The deviatory component is separate and the volumetric component is separate. The J relates the volumetric aspect. But in the compressible form model, the volumetric aspect is tightly coupled with the deviatoric part. Okay, it's not the deviatoric and the volumetric response is not separated out. Since they are tightly coupled, this becomes a really good model if you are dealing with foams, okay? Something like a sponges or a foams or a bubble wrap used in the packaging material or some other places. This becomes really a good model compared to other forms of hyperelastic strain energy potential. So since the principal stretches are directly used instead of the invariants, the curve fit becomes more accurate and it provides a better curve fit for a given stress strain curve rather using a strain energy potential which is in the form of I. Here it is directly in the form of I don't know how to put this, in the form of stretches. Okay. Again, one limitation is that if you have only a limited stress strain data, then this may not work good. We need the stress strain data for all different modes of deformation. Again, there are some guidelines given for different material constants which are nothing but alpha and mu. So what is the typical range expected for alpha and mu if you are in a small strain range, and if you want to capture the stiffening at the large strain range? These guidelines can be used during the curve fitting to effectively curve fit and find out the resulting values. Here are some more guidelines on Ogden model. Generally speaking, depending on how we tune this alpha and mu values, this may become very suitable for both small or large strain. You can tweak this model for better accuracy either in the small strain range or in the large strain range. So capturing the stress strain curve accurately in both small and large strain range become challenging. Here are the guidelines if you are dealing with some kind of foams and sponges. Typically the alpha value become large negative so that the compression effects will be captured very accurately depending on how drastically this alpha value changes. If it is negative, it will adversely affect the compression range. Like this, in the compression range you will see a drastic difference as you change the alpha in negative range. When you change the alpha in positive range, you will see the drastic change in the tension region. These are all the guidelines. Blasto model is another material model specifically meant for polyurethane foam type of rubbers. Here the Poisson ratio for this material model is predefined, which is at 0.25, which is a fixed value. And another important feature to note is that in all other previous material models, the invariants are separated into deviatoric part and volumetric part. Same thing, always we have used I1 bar or I2 bar. The bar used to represent the deviatoric part. But in this case, the deviatoric part and the volumetric parts are not separated, so that it becomes really good for capturing the compressibility effect, which is very dominant in foam kind of materials. So here are some guidelines on how one can relate the compressibility with the bulk modulus of the material for different Poisson's ratio. Here the Poisson's ratio is assumed as 0.25, so the bulk modulus becomes 5/3 times the shear modulus. This is a fixed relationship. It is found to be working good for 47% volume content of a polyurethane. So when we are dealing with compressibility type of behavior or incompressible kind of a behavior, having a clear feel for compressibility is very important. Okay, so you have to have a clear feel for how the strain energy potential, that is especially the volumetric part, is related with your bulk modulus and the Poisson's ratio. So here are some considerations for incompressibility. Typically rubber-like materials will have very small compressibility, so it is decent enough, or it is a fair engineering approximation to make the Poisson's ratio is 0.5 so that the material is incompressible. However, there are certain situations where even the small compressibility become very important. In such a cases, you can use nearly incompressible feature, so that you can assume the bulk modulus as 500 times mu, that will correspond to approximately 0.499, or when you assume the bulk modulus is 2000 times the mu, then you are going to limit of 0.5. Okay, so this is the approximation what you can make. 500 times the initial shear modulus or 200 times the initial shear modulus. As we have seen in the first part, more and more the bulk modulus, the Poisson's ratio is approaching towards 0.5. Again, when you are approaching towards the incompressibility, there is a high chance for shear locking or volumetric locking. You have to choose the appropriate element formulation, either the enhanced strain or UP formulation, which was discussed quite extensively in part 1 of this seminar. Okay, here are some basic relationship between the elastic moduluses and the incompressibility parameter, that is bulk modulus and the shear modulus that we use in hyperelastic materials. So it's quite important for you to understand the relationship. Vary this omega, this Poisson ratio from 0.3 in the increment of 0.3, 0.01 up to something like, make it a Poisson ratio here and bulk modulus here for a particular G value, and see how sensitive the bulk modulus with respect to Poisson ratio. Okay, you have to do this study in the Excel sheet to have a feel for that. And if you are working with Blasto or any type of a foam material model, and it is possible to relate the Blasto material constant, that is beta, to the regular elastic constant, which relates the incompressibility. Okay, so these are all the two important elastic constant which is related to the compressibility. So the Blasto material parameter beta this beta can be related to the initial bulk modulus and the shear modulus, so that we can have some physical feel, and also the beta can be derived from the Poisson's ratio itself. Okay, so for many of the materials, the material supplier will provide the initial shear modulus, initial bulk modulus. Those parameters can be used to derive the hyperelastic material constants as well. Extended tube is another very interesting and very advanced hyperelastic material model, which is based on the statistical mechanics. which is found to be very good for filler reinforced elastomers. The filler can be your carbon blocks or sulfur blocks and so on. Many of the practical rubber components do contain some kind of a filler reinforcement. So this is found to be very good for many of the practical rubber components. This particular material model is having the physical consideration in arriving the strain energy density function in considering the molecular scale. So what happens is that there are molecular chain cross-links. So when we apply any load into the structure, the chain gets stretched. Upon unloading, the strain comes back to the original shape. So in this particular model, we are going to consider what is the limit up to which this chain can be stretched, how much it can stretch. So that is called constraint boundary distribution modulus, and also we are considering the cross-link density. So this model can be thought of a two-term Ogden model when some of the constant takes the specific values. Okay, but this is more advanced than the Ogden material model. This is a very interesting approach and very relatively recent material model. It bridges the gap between the physics and numerics. All the material models which falls under statistical theory or the phenomenological theory, either they based on the physics or they based on the statistical approach. But this particular model bridges the gap between the two. It is quite interesting because it is very physics based. Unlike the other material models, it just needs 4 parameters to fit even the complicated stress strain curve. And again, the another advantage is that Ansys also have a curve fitting tool to derive these 4 parameters from the stress strain curve. Another interesting stuff, it is numerically stable and suitable for the extrapolation. These two terms will become clear when we talk about curve fitting. Okay, why it is important to have numerically stable material model and why we can extrapolate beyond the stress strain curve which is available from the test data. Okay, having discussed about the various material models available, now let us discuss about the curve fitting technique. So the curve fitting technique is available in both workbench interface as well as in mechanical APDL interface. So this screenshot shows the various hyperelastic material models for which you can use the Ansys curve fitting tool. Okay. Now look at that. When we subject the elastomer component to the actual loading condition, the different portion of the component may experience different stress state. So some portion may experience tension, some portion may experience compression, there may be a biaxial tension, shear, and also we need volumetric data to capture the compressibility related phenomena. Two important points to keep in mind when we do any physical test. The basic data are collected in terms of the engineering stress and engineering strain. For many of the nonlinear analysis for metals, we need to feed the stress strain curve in the terms of true stress strain curve for metals. Unlike metals, for elastomer components, we need to feed in the engineering stress strain curve to the Ansys software to do the curve fitting. So typically, to characterize the complete behavior of the material, we need these 6 different tests to be conducted. We need stress strain curve under tension, we need stress strain curve under compression, we need stress strain curve under biaxial, we need stress strain curve under planar tension, and so on. Now let us look at one by one. All these tests can be conducted experimentally. So this shows the typical testing setup for tension, shear, compression, biaxial, and so on. There are many standards available. So one such standard that I am familiar or commonly used is ASTM D412. You may refer this standard and understand how to prepare the samples, how to collect the data, and how to set up the test, and all those details. The first one is the simple tension test. So this is quite similar to doing a UTM test for any metal specimen, but the important part we need to keep in mind is that when we do the test, we must induce the pure tensile stress state in the material. So when we induce the pure tension, the material gets stretched in one direction, that is lambda 1. There will be a contraction in the another two direction because of the Poisson's ratio effect. If this stretches by delta amount in the loading direction, the other two directions are going to swing by 1 by square root of lambda times. That much it is going to swing. The simple compression is important. So one of the important challenge while conducting the simple compression is that the important point is that we need to induce pure compressive stress state. It means that when you compress it, this material should not stick with friction. This should slide like this. If it is sticking, then it will start bulging like this. Then the stress state induced in the material may not be pure compressive. Okay, so we need to avoid this. So there should be a proper lubrication provided such that the material expands like this. You can see that it is just a straight line here. It expands in a straight line. Rather, this material sticking here at the top and bottom, and it starts bulging. When the bulge happens, the stress state in the material is not pure compression. It is a multi-axial stress state. The studies has been done showing how the pure compression stress strain curve change as the friction coefficient increases between the fixture and your material. But for many of the practical cases, it is quite challenging to achieve friction coefficient of 0. There will be some minimum amount of a friction coefficient. This friction coefficient is going to make some difference between the physical test data and the numerical simulation test data or the results coming from Ansys. Okay, you just need to keep in mind it is highly recommended to provide as much as possible lubrication to induce pure compressive stress state in your material. The another one is the biaxial test. The biaxial test can be conducted on a rectangular specimen or a circular specimen like this, such that the stress is introduced in both the direction, and so in both the direction, if it gets stretched by delta 1 and delta 2, both these two are equal, there will be some contraction in the thickness direction, which is nothing but 1 by delta square. That's much the time the contraction will happen in the other direction. Shear, so there are basically two types of a shear. Shear has always been a very complicated mathematical expression when we are talking in terms of the engineering term and the mathematical term. Shear can be viewed at two particular aspects. One is the simple shear and another one is the pure shear. So in simple shear, what happens is that, so if you have a block of material, when you shear this like this line will get rotated like this. Okay, so the strain is induced due to the stretching of one diagonal and compression in the another diagonal, okay, which can be viewed as, this shear can be viewed as combination of stretching and compression, and also the material is rotated like this. This original flaws got rotated like this. The pure shear is something like when you pull this material, this part is going to stretch, something like this. Something like this is going to happen. So when you have a diamond like this, when you stretch, this material is going to shear. From this we can calculate what is the pure shear that has happened in the material. So the simple shear is something like this. It can be a double shear test or it can be a single shear test. This kind of a shear test is important when you design some components like this, something like an engine mount, which is typically expected to take the shear load. And when you are designing this kind of a product, this kind of a test become very important. But however, the simple shear test is not now commonly used in the industry to test the rubber component because of two simple reasons. First thing is that when you bond this rubber and this metal, it is very difficult to achieve a perfect bond. Okay, whatever the chemical composition, whatever the adhesive you use, no, even very tight glue material may not give a very perfect bonding such that we cannot introduce pure. See, there is a lot of meaning when I say pure. Okay, pure means there should be only one stress state in the material. There should not be any small compression, small tension in the material. It's very difficult to introduce a perfect bonding to see a pure shear. And the second reason is that as this displacement go up, this rubber will become very hard and hard, so that the plate itself can start bending. The plate start bending as you are imposing very large deformation, because the rubber is expected to undergo very large deformation, something like 100%, 200%. Then this plate itself will start bending like this. Then also it is not possible to achieve the pure shear state. So this is not used commonly for rubber. But however, if the product is under dynamic condition, which is taking up some kind of a vibration, if the vibration comes into picture, commonly the amount of displacement may not be very large. It may be few mm, something like 5 mm or 10 mm, may not be in the terms of 50 mm or 100 mm. In such a case, when the strain range is very small, then this approach may be the simple shear test may be suitable. But the simple shear is commonly used to test foam kind of a materials. Okay, the foam kind of material, though it is undergoing lot of deformation, the force required is very small, so that it cannot bend this metallic plate. But in case of a rubber, the force required may be very large, so that this the fixture plates can bend. Okay, for foam it's kind of suitable. So the most commonly used shear test is called a pure shear test. Though the geometry look like a tension, but in terms of the stress state, it has a lot of meaning. Okay, so when we have very large aspect ratio, a minimum recommendation is 10:1. Okay, if this is something like 10 mm and this thickness should be 1 mm. If we have a very large strip of material and if we stretch it and the material is going to undergo something like this, at this region there won't be a pure shear stress state, but when we move away from the end regions, in this region we will see a pure shear test. Okay, so later if you want, you can reach us through the technical support mode, write a service request in your customer portal and ask for this file. We can send you this file for you to familiarize the procedure. And to characterize the compressibility behavior, volumetric test is very important. Volumetric test is conducted with a button. So we will put a button, small button inside a constrained space, and we will try to compress this. What we will monitor is that change in volume against the pressure required to cause a particular change in volume. So this can be done in both in tension and compression, and you can calculate the volume ratio, because let's say if you have a specimen like a button like this in a rectangular cross section, you know the original volume, and depending on how much the plunger moves down, you can calculate the strain. From this you can calculate change in volume, original volume, and put it in x-axis. So for compression, the volume ratio decreases. For tension, the volume ratio goes more than 1. When there is no deformation, the volume ratio is considered as 1. It is not 0 here. Look at that. Again, when you are compressing the rubber in a constrained space, the amount of pressure required to make even the small change in volume is really high. But when we are stretching a rubber in a unconstrained space, though it is unconstrained in the box, as it stretches, the volume is going to shrink. So this rigid wall cannot offer any boundary. Okay, as the material is going to shrink, it can stretch. So for make even a large volume change, the pressure required is very less, which is very negligible. So it is a common practice to do this volumetric test only in the compression, not in the tension, because which is not very significant. Okay. So the bulk modulus typically is considered as this value. Okay, this pressure value. If this test data is not available, you can consider 2 to 3 order magnitude higher than the shear modulus of the elastomer. Okay. In the previous slides, we have seen how to calculate the initial shear modulus from the material constant. So when we are doing a curve fitting, there are 3 classes of materials. One is totally incompressible, which is Poisson ratio 0.5. The another category is nearly incompressible. In this case, the Poisson ratio is close to 0.5 but not exactly 0.5. And another one is compressible models, which is typically used for foam or metals kind of a thing. The first decision you need to make is that looking at this test data, whether your material falls under case 1, case 2 or case 3. Then once you classify what type of material it is, for case 1 and case 2, you need test data in uniaxial tension, biaxial tension, shear either in any one of the mode, if not the two, and the volumetric test data. Okay. For all these, the stress strain curve has to be engineering stress and engineering strain. Only for case 3, which is a compressible model, we need to provide lateral strain also additional input. Okay. For either purely incompressible or nearly incompressible material model, the lateral strain is not required as an input. When the Poisson ratio is assumed as case 1 0.5, volumetric ratio is assumed as constant 1, and we don't need this data when you are considering the case 1. For Blasto model, Poisson ratio is fixed as 0.25, so that we don't want to provide the lateral strain details. So for Ogden foam model, remember that both Blasto and Ogden are used for a foam model. For Blasto, the Poisson ratio is fixed, but for Ogden foam, the Poisson ratio is not fixed. So we need lateral strain information to account the compressibility if it is not known beforehand. Okay. Though we are saying we need 6 different types of test data, when the material is assumed as purely incompressible, there are some relationship exist between 2 different deformation modes. Say for example here, consider this is the uniaxial compression. It is compressed by lambda 1. We know that lambda 1 square plus lambda 1 square, lambda 2 square. This is the third invariant. Lambda 3 squared equal to 1. When it is 0.5, which is nothing but purely incompressible material. So when this is lambda 1, we can calculate what is the lateral strain, which is going to be the square root of lambda 1. Same way, when you have a biaxial tension, this is stretched in this direction by lambda 1. This being a biaxial tension, the lambda 2 is also going to be the same amount. Okay, these two are equal. Once we know these two are equal, putting this in this particular equation, we know that the lateral contraction is nothing but 1 by lambda square. We can use this relation to get a deformation tensor. This is for uniaxial compression lambda 1. These two are nothing but the deformation in the direction 2 and direction 3. For biaxial tension, we can write this relation like this, and this is coming from 3. Now we can see the principal stretch, this and this can be equated for these both cases like this. This can be equated. From this, we know that the stretch is nothing but 1 plus the strain. Here also we can put 1 plus strain. This is the biaxial strain. This is the compressive strain. From this equation, the uniaxial compression can be rewritten in terms of the biaxial tension. Same relation can be used for the stress as well. So once you know the compression stress strain curve, it is possible to calculate a biaxial stress strain curve. Okay. The point I am trying to make here is the value is not going to be the same, but once you know the uniaxial compression stress strain curve, it is possible to construct biaxial tension stress strain curve. Okay. So here is a typical example where the red color curve is the uniaxial compression data, and the green color is the biaxial data. One is the translated and another is coming from the test. Both match well. But remember, these kinds of the relationship is valid only for purely incompressible material, right? So as there is some amount of compressibility present in the material, there will be certain amount of error. As the Poisson ratio go away from 0.5, the error is going to keep increasing. Okay, this kind of assumption is valid if it is perfectly incompressible material. Assuming material is perfectly incompressible, which is valid for many of the rubber components, those 6 test requirements can be reduced into 3 test requirements. So the major 3 test data we need to completely characterize the stress strain behavior or the deviatoric behavior of any rubber component is uniaxial tension, compression and planar tension. If it is nearly incompressible, if it is perfectly incompressible, we don't need a volumetric test data. If it is nearly incompressible, we need volumetric test data as well to completely characterize the material. Having understood this, now let us look at what is happening exactly beyond the screen when you do the curve fitting. I will explain beyond the screen mathematics, considering a simple 2 Moody-Revlin equation, assuming only the uniaxial test data. Okay, let us assume you have a stress strain curve from the uniaxial test data. So what you have done, you have fixed the one end in the fixture and you are applying the tensile loading on the other thing. You got your stress strain curve. Now we know that we can write the strain energy potential for a 2 Moody-Revlin model, something like this. And from the basic definition of the elasticity, we know that the stress is nothing but the derivative of the strain energy potential with respect to strain. So this differential equation can be expanded using the chain rule as a derivative of strain energy potential with respect to the invariant dot product of the invariant times the stretch. So this is written as a chain rule using for first invariant and for second invariant. So when we differentiate this strain energy potential with respect to the first invariant, so this term will turn to 1 and we will get only C10, and this term will go to 0 and this term will go to 0. When we differentiate with respect to, this is supposed to be I2 here, and this is supposed to be 0, 1. I'm sorry about that. So when we differentiate this equation for this term dW by I2, so this term will go 0 and this term will become 1 and we will get C01. So we have these two terms calculated now. And again for the uniaxial tension, we know that in the tension direction it is lambda 1, in the other two direction it is nothing but 1 by lambda square. So now what we can do, we can substitute I1, which is nothing but lambda 1 square plus lambda 2 square plus lambda 3 square, and upon manipulation we will get the equation something like this. Similarly, I2 is nothing but lambda 1 square dot lambda 2 square, lambda 2 square, lambda 3 square plus lambda 1 square plus lambda 3 square. If we substitute this into this equation, we end up having this. Now in this equation we know both this term as well as this term. Substituting, if we take derivative of I1 with respect to delta 1, we will have 2 lambda 1 square. This will become minus 2 lambda minus 2, and we can also take derivative of this with respect to lambda. We will end up having these two equations. So now we have 4 terms, 1, 2, and we have 3 and we have 4. Substitute these 4 back into this equation, we will get C1 and C01 values, and here in this case 2 is common in both the terms. Take 2 out, and in this 2 is coming out, and we are taking again this term out, lambda 1 minus 1 by lambda square. This term is not present here, so what I'm making a common denominator here, so that this will become lambda 1 cube minus 1 by lambda square, and that becomes here, and this can be expanded like this. So this cancel out. So eventually what we are going to get out is this square term, this will cancel out. Eventually we are going to have only in the denominator. So we will end up having a equation like this. So this is nothing but the stress. In terms of the stretch is nothing but 1 plus the strain. So look at this. This is the equation we have. I am taking this equation here. What I am trying to do, again I am taking this term in the denominator, and we are ending up having a equation like this. This equation is nothing but in the form of y equal to mx plus c. So this c is nothing but this C01, which is nothing but the intercept, and this is m is nothing but the slope, and x is nothing but 1 by stretch. So the entire stress strain curve, whatever may be the complex stress strain curve, it is transformed into a linear equation, and we are finding the intercept and the slope of that linear equation. As I mentioned, though the 2-parameter Moody-Rowland equation or the material model is purely phenomenological model, but however it has direct relation, or rather saying a direct or some form of indirect relationship with the material microstructure. Here this intercept is related with cross-link contribution, how many cross-links that exist in your material, and the slope is directly related to the entanglement that is present in your molecular chain. Okay, so this is what is happening in the background when you do curve fitting. So in this case, I have explained what is happening beyond the screen, assuming only the uniaxial test data. But when we do the curve fitting, oftentimes we will supply uniaxial, biaxial, pure shear, either pure shear or simple shear. So the deformation gradient for different deformation mode can be written like this, and like we derived the relation between the stress and the stretch in the previous equation, we can derive the relationship between the stress and the stretch for both uniaxial case, planar shear case, biaxial case. Then all these three will become three linear equations. From these three linear equations, we are going to derive what are all those material parameter constants. Look at that. In one particular material model, I mentioned that this material model is directly the function of the stretch ratio rather strain. And also say because this is directly the function of stretch ratio, the curve fitting become more accurate compared to the other material models. The reason is that when we do the curve fitting, the equations are written in terms of the stretch ratio as you see here rather directly in the strain. So rather directly in the invariant. If any material model that uses the invariant, those invariant has to be again rewritten in the function of these stretches. So there will be some loss of information rather using a material model which directly relates to the stretch during the curve fitting. So what happens when we supply multiple material data? The curve fitting procedure is a trial and error procedure. When the curve fitting starts, it will assume some value for the C10 and C01. Once you assume some value for this, it is possible to reconstruct the stress strain curve. So once you know these values for different strain, this lambda is nothing but 1 plus the strain. Okay, you can construct the stress strain curve. The constructed stress strain curve in the first iteration may not match with your experimental stress strain curve. So at every data point, we can calculate the error. By minimizing this error, what we are going to do, we are going to bring the trial curve close to the actual experimental stress strain curve. So while minimizing the error, we use least square fitting procedure to minimize this error. This is again very standard numerical method. While doing this, we have two approaches. One is using the absolute error now, or other one is the normalized error now. When we use the normalized error now, what happens is that whether the strain is at a very low strain range or at the high strain range, it will give same weightage for all the data points that you have. When we use this one, when we use the absolute value, there is more weightage given for fitting the data at the higher strain range rather fitting the data at smaller strain range. Okay, so depending on the situation you have to use. Say for example, when you do the test, your data might be something like this. You may have a very large gap at the lower strain ranges, but you have very close data collected at the higher strain ranges. Okay, or your case may be the other way also. You might have a lot of data at the very low strain ranges, but there will be there will be only less number of data, there will be a large gap at the higher strain ranges. So depending on how the experimental data is collected, you have to make a choice whether you want to use the absolute or normalized. If you have equally spaced data, then the default normalized error minimization will work good. But if you have data like this, you have only less number of data at the higher strain range, but your interest is also to capture the results correctly at the higher strain range, then it is recommended to switch from normal to absolute minimization procedure. The curve fitting becomes more and more complex. How accurately we can fit this curve depends on how complex your data is and how many coefficients you want to find. Okay, so this table shows for different material models how many coefficients you need to find. Some curve fitting procedures are linear, which is quite simple. In other words, the resulting accuracy of the curve fitting not very highly depend on the initial values you provide, but for these material models which require nonlinear curve fitting, the result of the curve fitting parameters highly depend on the initial values that is provided for the iterative procedure. So that is the reason in the previous slides we have given different guidelines for different material models. So what should be the initial shear modulus, how the different constant related to the different portion of your stress strain curve. So you have to really relate those guidelines in providing the initial values for these nonlinear curve fitting material models. Again, there are a lot of care has to be taken while collecting the experimental data. You might have tested the data for multiple cyclic loading, but these cyclic stress strain curve cannot be used to do the curve fitting with any of these hyperelastic material models. So we have to come up with a equivalent monotonic stress strain curve, something like shown here. So these data preparation steps need to be done outside the Ansys. Let us say this black color line represents the test data that you got from test lab. From this you have to find out a monotonic stress strain curve, and again this stress strain curve has to be fed into the Ansys. And sometimes though you do not subject your specimen to many cyclic loading like this, it may be a one loading and unloading, but this material may show some kind of a hysteresis behavior. But again from this curve there are two curves from the test data. From this you have to find out one particular curve out of this. You may choose to use the loading curve or unloading curve, either the top curve or bottom curve, or you may take a mean. This kind of judgment will come by experience. Okay, so as a software provider, it is very difficult to recommend you have to use the first loading curve or first unloading curve, or you have to use 100 cycle curve or a 200 cycle curve. That you will come to know as you are gaining experience in this particular field. To do a better curve fitting, it is important you know your material and your product well. You should know what is the purpose of the product you are designing, and what are all the deformation mode that the elastomeric material can undergo when the product is put under service, whether it is going to undergo shear deformation, or it is going to undergo the biaxial tension, or it is undergo only the pure compression. You should know the deformation mode that the product is going to see when the product is in service. and also you should know your material. You should have some basic idea about why SBR rubber is chosen for this product, why not the EPDM metal. Okay, you don't want to know what is the exact chemical composition for the EPDM, what is the chemical composition for SBR or NBR, but at least one is expected to have why NBR, why not SBR, those kind of information. Okay, so it is all, you should know little bit information about the method of manufacturing, whether it is vulcanized or what kind of a filler components are there, what is the curing procedure used, and what is the loading history, whether it is going to undergo only one loading, it will like a seal, or whether it will be subjected to a cyclic loading like this, again and again it is subjected to a cyclic loading. Environment condition, whether it is going to operate at 20 degrees Celsius or 200 degrees Celsius, depending on that the stress strain curve will be completely different, and the environment you need to test will be completely different. So knowing your material and product is very important to decide the testing program that you need to tell your lab. Okay, you conduct this kind of a test for your material. Another important criteria is the stability criteria. So typically it's called as Duker stability criteria. Rather me explaining this in mathematical aspects, let me try to put it in a physical aspect. For any finite element model to work, as the strain increases, the stress need to be increasing. Okay, your stress strain curve, like even in the metal, we cannot capture the stress strain curve in this portion, because what is happening in the sense, in this region, as the strain is increasing, your stress value is coming down from this value to this one. We cannot capture this. This is called negative slope. So when you do the curve fitting, say for example, this is you have your stress strain data for let's say a compressive test. The data are plotted in the positive coordinates. When you plot this, you will get some C10 value. If you put this C10 value into this equation, let's say this value is 0. Put this equation, you can generate the stress strain curve. The generated stress strain curve looks like this for a very large either you can think that as a lambda or an engineering strain. Look at that, up to somewhere close to 50% of the compressive strain. As the strain increases, the stress is also increasing. But after this limit, as the strain increases, the stress values start reducing, which means that beyond this region, your material is not stable. It means that you cannot compress this material in Ansys beyond somewhere close to 50% compression. Okay, that's what it means. So when you hit the solve button in Ansys, using if that finite element model involves any hyperelastic material, Ansys does this check automatically up to 10% of the stretch. If there is any particular deformation mode that becomes unstable within this 10% of the stretch, it will print the warning for all 6 different modes. So in this case, I am giving one example. Out of all the 6 possible modes, it has printed only 4 modes. It means that there is no stability issue in the uniaxial compression and the equibiaxial tension, which is not printed here. For all other modes, if the stretch value goes beyond this particular limit, the material will become unstable. You may not able to solve the problem. There are some material models, as I mentioned, which are very stable. Okay, like Neo-Hugin model is always stable. You don't want to worry about beyond this stretch value whether it is going to be stable or not. There are some places to improve the fit in one particular mode. Depending on which mode is predominant in your product, you may have to sacrifice fitting the curve in the other modes. Okay, say for this example, if you are designing the bridge bearing, if it is purely undergoing a compression, you may choose to discard biaxial and the shear test, which is not, the product in service is not actually undergoing the shear and biaxial, so you can try to achieve the good fit only using the tensile test data. Or in other case, if it has only the shear, you can remove this uniaxial data, use only the shear or biaxial test data, and you try to achieve the better fit for one mode. It may not be possible to achieve better fit for all the modes, as curve fitting is also a kind of art rather just the science. Okay, it is as much as art as science, so you have to do some compromise, but oftentimes it is not possible to get 100% fit for all possible modes. Some or other way, when your stress strain behavior is complex and also you are interested in capturing the large strain range, some place you have to make some compromise. Okay, and some of you don't have any idea about the material testing and so on. There are some literatures available where the value of 2-parameter Mooney-Revlin constant given as a function of rubber shore hardness, which is one of the very important design parameter. Okay, the moment you talk about rubber, the specification always includes the shore hardness. For different shore hardness, the values of the C1 and C0 are given in some literature. You can look at the literature, but again the values here are very unrealistic. Okay, if you compare the recommendation from 3 different literature, the values are very highly varying. And also the idea of me showing you this is that not to encourage you to go and use this constant for your rubber which is having 40 shore hardness, because the 40 shore hardness of EPDM rubber will behave entirely different from 40 shore hardness of NBR rubber. So the idea is you go and test your different rubber components having different shore hardness and come up with a database like this for your own material, so that you can use this database for your future purpose. Okay, again I repeat, the values shown here are just to encourage you to develop the database for your own materials for different components, not Ansys is recommending using these values. Okay, these are all very unreliable values. And also remember this relationship. Okay, once you know the material constant, you can calculate what is E and G. So in summary, when you want to really capture the complete material behavior of the rubber, you should prepare a sheet of rubber material and cut different specimens from the same rubber sheet for tension test, pure shear test, equibiaxial test, for volumetric test and so on. Conduct all the experiments and look at the raw data, process the data and arrive the data that is useful to do the curve fitting. In general, the 3 data are required. One is uniaxial tension. In the tension, the material will exhibit most soft behavior. Okay, it means that to produce particular strain value, the amount of force required in the tension mode is very less. In the compression, the value is going to be very high. It means that out of these 3 curves, the good idea to test whether the stress strain curve makes sense is that your compression curve should always appear in the top, your tension curve should always appear in the bottom, your shear curve somewhere in the middle. Okay, either it should be like this or it can go like this, but at no point your uniaxial compression curve can come below the uniaxial tension. Okay, these are all some quick sanity check if you are getting the stress strain curve for a different mode from somebody else. You can look at just the stress strain curve and see whether this stress strain curve makes sense or not before you feeding it to Ansys. So before running into the solution, it is highly recommended to pay attention to your output file, look at the stability check, look at up to what strain range or the stress range your material model is stable. Don't try to apply a force or displacement which will take your material beyond the stable strain range. And also it is important that Ansys giving you a stability warning not necessarily mean a failure. Okay, there is a high chances that you can't convert the problem due to this limit. Go and revisit your material model. Okay, so improving the fit in one deformation mode shall make the another deformation mode become unstable. So you have to make a balance between the accuracy in the curve fit and making your model stable. There are some places you have to compromise little bit on accuracy but make your material model stable so that you can get more insight about your product behavior rather looking at the exact numbers, whether the stress is 2 MPa or 2.0 MPa. That is not very important oftentimes, but you need to really understand whether that piece of material is in tension range or a compression range. That is possible by compromising little bit on accuracy, but it may not be possible by making your material unstable. Okay. So it's like, as I mentioned, it's like a balance between the accuracy and trade-off, and curve fitting is art between art between the engineering and curve fitting with precision. Another interesting material model is the response function model. The main advantage of the response function material model is that you don't want to use the curve fitting at all. It will straight away use your stress strain curve to track the response of your material. Okay. So what we do is that from the previous derivative we know that we can write stress in the function of strain energy potential derivatives. These derivatives are called as response function. Okay, so this is first response function, this is the second response function. Now we are going to write the stress strain curve in terms of the response function. So this response function model is also called as a Marlowe material model. In other tools or in the literature, both are the same. The exact way it works is like this. Once you know the strain invariance, you know the deformation state, you can write stress in the function of the strain invariance. The derivation is almost same as that of the previous derivation that I went through in detail. As you can do it for uniaxial case, knowing the deformation tensor, you can do it for biaxial or shear for any relationship. Okay, so here from the test data we know the stress, we know the stretch. Okay, the stretch is nothing but 1 by strain. The strain is coming from the test data. So the unknowns are these two invariants are the unknowns. So these two invariants are calculated. Here are the example. There are two response functions. First invariant based on second invariant. So to determine two invariants, we need more than one test data. If we have only one test data, using one equation we cannot determine these two parameters. So these parameters are determined from different test data. So we need more test data, more than two. If we have only one single set of the experiment, we set the second derivative as 0, so that we need this term is set to 0, so we have only one test data, we need only one unknown that can be predicted. So if we are having two test data, then we can calculate exactly this and this. But assume a scenario where we have all the three test data. We have both uniaxial tension, biaxial tension, and pure shear. In such a case, we have two unknowns but three equations. The equation become kind of a under constraint equation. So what we will do is we will use the best fit among the two response function that is derived from three experimental data. And also the response function model can be used to model both combined tension and compression curve in the single thing. Okay, for all other material models that we have seen so far, the uniaxial tension and uniaxial compression has to be supplied as two different test data. For response function model, we can combine both uniaxial tension plus compression in single test data. If we are using that particular test data, we cannot combine this with either biaxial tension or pure shear. If we have combined tension plus compression, only the volumetric test data is allowed to combine with that. We cannot combine any other thing. If we want to combine both tension, compression, uniaxial tension and compression, biaxial tension and pure shear, then we have to supply tension as a different test data, compression as a different test data. We cannot combine into one single test data. That's an important point you need to keep in mind. And again, when we are using both combined tension and compression, we can supply pressure volume relationship to characterize the compressibility of the material. So the equation that I shown here is not considering the compressibility factor because the volumetric part is not included, but it is also possible to include the volumetric part for both uniaxial, biaxial and pure shear. The equation becomes little more complex. I don't think we have sufficient time to get into the details, but if you have understood so far what is happening beyond the equation, I think I'm fairly confident that you can go and crack what is happening beyond this equation. So as I mentioned, this response function model can be used to model combined uniaxial tension plus compression along with the pressure volume data for capturing the compressibility. This can be used to model different stress strain curve for the metals also. Okay, the metal typically having the Poisson ratio of 0.3, so we cannot consider the metal as an incompressible material. So we have to use some kind of compressibility which is accounted through lateral strain and pressure volume relationship. So this model works well for a small strain range, but when the strain range becomes large, this is not going to work pretty well. Say, look at the example. When you introduce the compressibility in the response function model, this is the block curve which is actually deviating from the engineering test strain data. When you introduce compressibility, but again the problem occurs only at the large strain range, which is more than 50%. But for a compressible material like a rubber, which is compressible, which is incompressible like rubber, we can use this response function material model even for very large strain range, which will exactly capture the material behavior. The limitation is that with metal which is having a good compressibility, we cannot use that at very high strain range. But typically when we are dealing with metal, we are limited to 4 or 5% strain, wherein assuming some compressibility is also giving a very good result. So this response function model can be used to capture a different stress strain behavior in metals also. But again, remember that the nonlinear behavior is not plastic part. It is inelastic, but we cannot say that as a plastic. Remember, it is inelastic but not necessarily a plastic deformation. So the way to feed this is straight away feed the stress strain curve for uniaxial, biaxial, shear and volumetric if it is nearly incompressible, and use that. It does not need curve fitting, and again the important limitation is that if you have your stress strain data up to let us say 50%, you cannot use this material model to analyze your component up to 70%. You cannot really use this material model beyond the test data which is available. Okay, you can use this to analyze any component up to 10% strain, 20%, 50%, but not more than 50%. We cannot use that. I was mentioning when you are using the extended tube model, I mentioned that this is a very reliable model, but it is also suitable for extrapolation. When you use extended tube model, though it requires curve fitting procedure, if your test data is available only up to let's say 50%, you can reliably use to analyze your component even up to 100% or 200%. It might give you a reliable data, but little you go away from your little the extrapolation, your results are going to be more realistic compared to the test data. So far we have seen various hyperelastic material models, but in reality the actual rubbery materials or elastomer exhibit both elastic and viscous material behavior. The hyperelastic material model, so far we have discussed, capture only the elastic part, which means that which is really suitable only for a monotonic loading. It will not capture what is going to happen when you unload it. It does not capture the hysteresis during the unloading, which is quite normal in any rubber, and also which would not happen the strain rate effects. Something like when you load it at 10 mm per second, what is the difference? When you load it 100 mm per second, what is the difference? And also when we say the strain rate effects, time dependent behavior, and also it will not capture the virgin material damage, permanent set, which is quite important in ceilings kind of application. So all the hyperelastic material that we have discussed so far, good only for time versus force, which is linearly increasing in whatever, which is increasing linearly. The moment it is undergoing some kind of a cyclic, which is not good. So to capture that, we have to use different kind of material models along with the hyperelastic material models. The first one is called popular Mullins Effect. The Mullins Effect is useful when you are subjecting a cyclic loading. The loading curve and unloading curve will not follow again and again the same stress strain curve. The basic assumption we made for hyperelastic material is that the loading curve and the unloading curve is same. But for many of the elastomery component, it is not going to be like this. See, when you load it, it will go like this, but when you unload it in the first cycle, it will follow the different curve. When you load again, it will follow this curve, the return curve, and it will join with the parent curve. It will not going to follow the parent curve. It will follow the monotonic curve. Again, it come back from the zero. Then again, when you are reloading, it will follow this path. This can be characterized using Mullins Effect. This will capture the material softening behavior during the loading. Though what exact phenomena is causing this softening behavior is not exactly known. There are thoughts that this is due to the debonding, like the debonding happenings in the polymer chain, or it's a rearrangement of the polymer chain like this. This can be caused. So this phenomena can be captured using Ogden-Rasberg material model that is available in Ansys. So the basic idea for this one is that this is the virgin material strain energy potential. The virgin material strain energy potential is augmented with some damage. when this damage is equal to 1, it is nothing but the virgin material, there is no damage. But for different material, we can write the damage as a function of certain material parameters. So what we are going to do is that the damage is written as a function of what is the maximum strain energy that exists in the previous cycle, such that we can predict the amount of damage that is happening to the strain energy potential over time. To capture this, it requires three material parameters, R, M and beta. These can be calculated from the stress strain curve, and this can be input into Ansys using following command snippet. And using this Ogden-Rabsburg material model, we should be able to predict this cyclic damage that is happening in the material. There is a nice example available in Ansys training material. You may have a look at it and understand the procedure. The other important phenomena is hysteresis and the permanent side, especially when you are using a O-ring for a sealing application. The material always exhibits some kind of a permanent side. This can be predicted using the Bridgestone-Boyce material model available in Ansys. This material model assumes that the material is a combination of elastic and viscous model, and so what happens is that in the regular hyperelastic material, we assume that the molecular chains are getting stretched upon the loading, but when you reload it, it will come back to the original position. That is what the regular hyperelastic material will do that. But this Bridgestone material model will assume that it is not coming back to the original state, but it is attaining a new relaxed position. Okay, it is somewhere in between this shape and this shape. That is due to the viscous component. So using this material model, we can capture the strain rate dependencies, relaxation, creep, energy loss, permanent side, and so on. Here, both the spring and damper are highly nonlinear, which are formulated using a relatively complex equation like this. So the total stress in the material is considered as a part of elastic response and part of viscous response. This is also having the strain rate dependency. Here what we are saying, the stress is not only the function of deformation, but it is also the function of rate of deformation. It means that the viscous part has something like a statistical mechanics approach material model, which will capture the elastic part, and there is a viscous part. So there is a viscoelastic response and there is a equilibrium response. That is nothing but A. A is a equilibrium response. This is a viscoelastic response. There are the terminologies used here is same as that for the B term as well. There are 8 material constants to capture the deviatoric behavior, and other one parameter to capture the volumetric parameter. And this material model itself is a complex to capture both elastic equilibrium as well as viscoelastic response. This particular model cannot be combined with any other material model, because if appropriate test data and understanding is there, this one material model can capture both the equilibrium response as well as rate dependent response. Unfortunately, the material curve fitting for this material model is not available in Ansys, but there is a quite elaborative procedure explained in the Bridgestone PhD thesis, and also there are niche softwares like mCalibri or Hyperfit software can be used to determine these constants from the stress strain data. So to predict the permanent set, here are there are 9 constants as I mentioned, 8 plus 1. Here are some guidelines. The constant C5 is kind of inversely proportional to the permanent set. Okay, it means that higher the value of C5, the permanent set is less. So in reality in your product you are seeing a more permanent set than what is predicted by the simulation. It is an indication that you have to reduce your C5 values. Similarly, there is a guideline given for C6. Again, the C6 is having an inverse relationship with your thing, but whereas C7 is having a linear relationship with your permanent set. So you have to increase your C7 value to predict more permanent set or more hysteresis loss that you see. So again, there are examples available in the training material to understand the permanent set and also to understand the hysteresis loss. The permanent set is very important while you are designing O-rings and seals, because there are guidelines says that only 50% is allowed for a compression and 50% in the shear. So these guidelines has to be accounted along with the permanent set. Okay, it's not only due to the loading, the permanent set effect also need to be captured, and this is again become important aspect of it. There are certain class of materials like human tissues or some artificial biological elements used to model robots, or especially this is one example where the fish robot is modeled with some kind of a flexible material which is having orthotropic properties. Those can be also modeled using Ansys hyperelastic material models. Though we are not discussing in detail in this presentation, I just want to give you a heads up that this can be modeled using Ansys. And we have seen many hyperelastic material models. As I mentioned, for certain stress strain curves, more than one material model can result into the same response. There are certain stress strain curve which cannot be captured using all material models. There may be one or two material model which will capture your response well. So it is important to do the trials with various material models and identify which material model is really suitable for you. And also all these material models are developed over years, starting from 1940. There are certain material models which exist only for the legacy reasons, but the very recent material models can encapsulate all the advantages of the previous material models. There are different papers published from various universities and industries by comparing various material models and its usage and other things. So what I'm trying to do here is summarize the outcome of those studies. Again, I want to insist the point, these are all not the studies done by Ansys or recommendation made by Ansys. This is the summary of various research papers. The summary says that the extended tube material model and response tube material models are two most advanced and efficient material models. Okay, so though there are many material models, they exist for the legacy reason. My recommendation is that if you can do a curve fitting for extended tube material model, use this as the first choice, response function model as the second choice, or this may be the first choice. You have the stress strain data for the entire range of material that you are dealing with. If you want to use the legacy material models, Moon-Irwin model or Neo-Huygens may be the choice. If you are dealing with the foams, then you have to use either Blasto or Ogden foam model for that. That's the choice. Here are some important relationships that you need to remember if you are working with rubber analysis. This will become very handy to get the physical feel for your material parameters in terms of the elastic modulus or the Poisson's ratio. As I mentioned, we have touched upon the various material models to some extent in this presentation, but the complete theory is available in the help manual. You can go and refer the help manual to gain further deep understanding on this subject. There are a lot of solutions available in customer portal. You can refer this solution to gain further tips and tricks. These are all 3 books that I would recommend you should buy and start referring if you are into design and analysis of rubber components. There are plenty of knowledge materials available in the customer portal. You can go and search with Hyperelastic. You will get so many guidelines and the procedure, and also the complete nonlinear material training model material is available along with the workshop in the customer portal. You may download and start practicing that. Many of the guidelines and the content in this presentation are taken from these training materials. Often the contacts and the convergence issue go hand in hand with rubber. This is one classical and very complicated analysis example to deal with rubber, hyperelasticity, the convergence issues. To gain complete, to master yourself in the rubber analysis, you should have good understanding on the element formulation, material models, contact and convergence procedures. In the next part of the series, part 3, I'm hoping to offer some insights on contacts and convergence procedures. In next year, I hope to see you, reach back to you next year on these topics. With this, I close my presentation.